So over the last few weeks, we've been going over a lot of approximation schema, and one of the ones we're going to do this week is called the WKB approximation. So WKB, in WKB approximation, just right up here. So the WKB, they're just three guys. I think it's, Wenzel, Kramers, and Berlin. And these three people are just collaborators. But what this approximation schema does for us is it helps us solve the time-independent Schrodinger equation, which I know it's kind of hard to solve for different and varying v of x. So they try to think about one. So if you're not familiar, which I'm sure you guys all are, so this is our time-independent Schrodinger equation, and this is what WKB approximation aims to solve. So let's try to follow our principles initially, and let's try to think about something that we know the answer to, okay? So that's always a good place to start from any approximation scheme. So let's try it. We'll start with a potential, and let's say that it's actually a constant potential. It's just a flat line somewhere above the x-axis. So here's our v and here's our x. And we have this energy, this particle that's in this little, in this potential here, and it has energy higher than v. So we can see that E here is greater than V. Now, if we have this kind of similar potential, we know we can solve it, right? We've solved potentials like this before. For instance, the infinite square well potential. We know all the solutions to the infinite square well, and that's basically the same thing. It has a constant V at the bottom, and E is usually somewhere above that, okay? So let's try it out. Let's just run it by our equations, and actually we do get very similar equations that we're used to. We get something that looks like this: psi of x equals E, A E to the plus or minus I k x. Now, if you guys haven't seen this, I'm sure you guys are familiar with it. This is just a complex exponential where k we define to be equal to the square root of 2m e minus v over h bar. Okay? So this is just our amplitude of the wave here, k, that's our wave number. Okay? So these are is our complex exponential solution to the case where e is greater than v. So now what else can we do with this, right? Let's try to consider something where e is less than v, okay? So here's what I'm talking about here. I'm taking a new particle now, and let's try to see if we can understand what happens if e is less than v. Well, if e is less than v, there's a new e. This doesn't apply anymore, but we'll just keep it here just for reference. Okay? Now, if e is less than v, what do we get? So let's do it over here. E is less than v. It's kind of a similar equation, right? Again, we know how to solve this. So all we see is that our psi looks like this. Psi of x equals sum A, sum amplitude, e to the k x, plus or minus. Now, these plus or minuses, if you guys remember, those plus or minuses are just, they're two different forms where plus is going rightward and then minus is going negative. And then, but this time our k changes, right? So our k changes this time, giving us square root of 2m. Now what changes here? E is now less than v, okay? So if e is less than v, then this will give us a negative number. We don't want that. So we'll just call it v minus e this time, over h bar. Okay? So now we have two different equations here, but they're only differing by what we consider to be greater. So in this case we consider e to be greater, in this case we consider v to be greater. But either way, we get a similar exponential sort of function that we're kind of used to seeing in this example. But now, this is kind of where the root of WKB comes in. Well, you guys probably should remember these two equations. We might come back to them. So if you guys want to write those down. But now, let's consider something else. Well, maybe, just maybe, we have a different potential. So let's say we have, so here's our x, here's our v, and what should we say now? Maybe our v is now not constant. So maybe our v kind of goes up, just slightly, all the way out, okay? So it goes up and up and up, but we can see that it's almost like around here, and here, right? Across these places, it's kind of constant. So maybe we can do something with some similar answers that we already know of. Well, first, let's consider this function here. So we'll have an e, that's, well, let's say it's I. Okay, so our e goes out here. Now, what would a function, our wave function, look like? If we were to draw it out, what would our wave function look like? Well, let's try to draw it out. In here, it's got kind of low, so it probably has a high amplitude here. But then you see that v affects it more and more as you go out, right? So v is kind of taking up more of that energy as you go out. So the amplitude is kind of going to go down every time. Now we can see that here, like x1 and x2, we have different lambdas, right? We have also different wavelengths, right? We kind of lengthen. So we have x1 here and then lambda of x2, maybe here. And now we can see that it goes from tighter to like longer. And what we're saying here is, let's assume, to kind of solve this equation, maybe we kind of have to figure out what lambda is, what's happening to the wave function as it interacts with this v. So to do that, let's kind of assume something about what's happening with this v. Let's assume that for our case, this v varies only slightly compared to our wave number. So let's just say it varies slightly to 1 over k. Right, so our wavelength is varying only slightly with respect to k. So as k changes, so v is only changing very slightly with respect to our wavelength here. Okay, so now this is the root. This is the root of the WKB approximation. We'll come back to this a lot more. So this is what we're trying to say. We're trying to say that for any v we have, that it only varies slightly with respect to our wave number. And then from this, we can back things out, right? We can get that our lambda is equal to, right, it's 2 pi over k, but this time k is changing, right? K is changing. So let's actually say that lambda, normally it would just be k down here, but let's say that lambda is also varying with x because k varies with x, okay? And now we can say now k of x, in this case, we've defined. We can define it in a similar way that we did before. We can say that it's the square root to m. In this case, let's see, our e is higher than our v, so that must mean that we get this e minus v over h bar, okay? But now here, note that this is our normal k. But what's different here is that our k now depends on x, because our potential depends on x. So that's the main change we're going to do here. And these are kind of the base formulas for the WKB approximation. And that's where our assumptions will all come from later. Now, let's consider the real meat of this approximation scheme. Let's kind of solve some problems, right? So to begin, I'm only going to consider things, particles specifically, in something I like to call the classical region. So later we'll go over things that aren't in the classical region, but what do I mean by this classical region? So let's assume we have this potential again, start up here, maybe we come down here, and come up again. So, and we have our E, so what's our E look like? Our E looks like something right here. And now we have these points here that I didn't kind of mention earlier, but you should be kind of questioning yourself with the way we formulated K before. What happens at those turning points? Well, later we're going to kind of cover that more. So let's just not worry about that, and let's worry only about what's inside here called the classical region. And it's called classical because we understand what happens there, right? If there's a particle in a potential well, it's just kind of going to rock back and forth and kind of going to go only in here. It's not going to leave. Okay, so that is where our E is greater than our V. So that's what we call the classical region. So now, let's kind of rewrite our Schrodinger equation in this classical region to see what the WKB approximation that we made does to the wave function. So, what does our wave function look like? Well, what does the Schrodinger equation look like? Moreover, sorry. So the Schrodinger equation, we wrote it down before, so we know what it is. Let's try to write it again. Let's go negative h plus over 2n. So here's the change, right? V of x is now a function of x. So V, our potential, is now a function of x. Psi equals E psi. Okay, so there's our equation. And now we have this V of x, this varying potential. And what does that do to the Schrodinger equation? So from that Schrodinger equation, we can kind of take a step down and try to solve it out. So if we just do some kind of maneuvering with all this, we can say that this, we can kind of isolate this and say that d psi dx squared equals p of x, I'll tell you what that p of x is later, over h bar squared. Sorry about that. So h bar squared. Now, what is this p of x? Well, you kind of just lump that in there. Well, p of x, we can just define it as anything, right? So p of x, we can define it as 2m, let's say, see what I have here, e minus v. Just as I said before, e minus v of x over, well, over nothing, right? Because we already have this h bar squared, so we don't need that here. Okay? So, and this, if some of you guys might recognize as what we call the classical momentum. So it makes sense that we're getting something that we call the classical momentum out of what we've considered, which is indeed the classical region. Okay. So from this, how could we solve this equation? Well, let's first assume something again. I know we're always assuming here, but it actually seems to be really helpful. So I'm actually going to write it down here where you guys can remember it. So we're going to use this ansatz a lot. Psi of x, we know it's got to look like something that we might have seen already. So it's got to look like a complex exponential, right? Because when we did this before, on a constant potential, we got a complex exponential out. So maybe if we're doing this approximation where we say that it's almost constant, then should we get something that's kind of similar to complex exponential? And in fact, we do. So let's assume this, A, but now our amplitude, it's going to depend on x, right? It's going to have to because our v is changing. So our A has to change with it. And then E, the plus or minus, I. Now here is something more interesting as well. We said that also the wavelength changed, right? So because the wavelength changed, what else can we put here? We can't have really a k that's constant. So let's just call something called phi. We'll just call that, let's say that's the phase of our wave function. And now our phase of a wave function also depends on x, right? Because again, our v is changing, so our phi and amplitude are both going to kind of change with that. So this we're going to use a lot more. So we're going to use this several times, so you guys might want to write that down just as an ansatz. If I say we're going to use the ansatz from previously, that's what I'm referring to, okay? So we're going to do this. And let's also, I'm just also going to say we're going to use the kind of formalism where f prime of x equals df dx, okay? So we're going to use this kind of formalism just because I'm not going to keep writing this all the time. And I'm going to say, using that ansatz, what does psi prime look like? Well, using that ansatz, psi prime has to look like a prime plus I, a phi prime, e to the I phi, okay? So here we have our first derivative, but in our equation here we have the second derivative. So you just got to separate it there. So we have our second derivative, so maybe we should find the second derivative while we're at it. That might be useful. The second derivative gets a little bit harder, but again, it's just another chain rule and another chain rule and another product rule, right? So it's kind of not that hard to find out that it's a double prime plus 2I a prime phi prime plus I a phi double prime minus a phi prime squared, all times this e to the I phi. Okay, so this is our double derivative, and I know it looks kind of complex, but we're going to use it and try to simplify things a little bit later. So is it all right if I erase this kind of stuff? Has everybody got it? Okay. So guys, remember this. We're in this classical region, and we're going to use this ansatz again. And again, we're using that formalism. So from this, let's plug that into what we got for our Schrodinger equation. Okay. So now we have kind of everything working out with us. We'll plug that back in, and we'll see that one side we have this, right? This phi double prime, and the other side we kind of just have this p of x over h bar squared. So we're just kind of going to keep that. But remember, this is also times psi. Sorry about that. I didn't catch it the first time. But so if we kind of mess with these things, the psi remains. So I kind of forgot about that the first time I wrote it down. But there is a psi out here. So we're going to say psi is our ansatz before, okay? So let's plug it into this equation, this star equation. Now what do we get? We get a double prime plus 2I a prime p prime plus I a phi double prime minus a phi prime squared. Now that's our partial derivative that we found here. Now let's plug in the other side. It's going to be negative p squared over h bar squared. And what do we also have this a out here, right? So what I did here is I just divided both sides by this e to the I phi, because we had an e to the I phi here with our first ansatz, and then we still had an e to the I phi on this side with our partial differentiation that we solved earlier. Okay, so from this, let's break it up, right? Because we can obviously see here there's some imaginary parts on this side, but there's no imaginary parts on this side, right? So we can say that's like plus 0i, and we get kind of two equations. We get this real equation here, and the real equation looks like this: a double prime minus a phi. It's a double prime minus a phi prime squared equals, well, this isn't imaginary, so let's keep that as well, minus p over h bar squared a. Okay? So that's what we get on the one side, and then on the imaginary side, write it down here. So on our imaginary side, what do we get? We have this 2i a prime phi prime plus, oh, sorry, our i's cancel because we can cancel out either side of the i's. But we get a phi double prime equals 0, right? Because we had no i's on that side. Now this second equation here, we'll call this imaginary. We'll call this the second equation. Let's call this the first equation. Okay. Now this second equation, it's pretty easy, right? We've all seen this in partial differentiation before. In our differential equations class, we've seen this before. And it's easy to solve because we can make the statement that squared phi prime is this whole thing, right? If we do the kind of chain rule on this, what do we get? We get 2a prime times phi, okay, that makes sense. Plus, because of product rule, we're going to have another a phi double prime. Sorry about that, I forgot my primes up here. So actually, there's a prime here and a prime here. So everything works out, right? Equals 0, okay? So we have this primed equation equals 0, which you guys should be plenty familiar with. And I'm just going to do some inner working here, just turn the mathematical crank, and I'll give you guys the full answer. A squared phi prime equals some constant, right? We integrate both sides, and then we get a is equal to c over phi prime. Okay, so we get this c over the square root of phi prime. Do you guys see where I got that? Because we can absorb this square root into c and kind of it disappears, okay? Now this second equation, let's see what kind of manipulation we can do to this. We kind of want a on one side. We can kind of move this a double prime on the one side. We can get a double prime equal to negative p over h bar squared plus phi prime squared a. Okay, so I pull out an a, and now we kind of have something. We have a double derivative and this single derivative, this original function on one side and the double derivative on the next. Now this kind of is a little hard, right? This, you guys might remember from differential equations, is not that simple to solve. We'll see that this is actually very trivial. This is the right answer for this one, but this isn't trivial. So let's try to work it out over there. If you guys don't mind, I'm going to erase what I have going on over there if you guys can remember. Just remember that ansatz and stuff. I'll write it down again if you guys really need it. Let's see. Okay. So now from this, let's move this equation over here and kind of figure it out because it's kind of getting confusing. So to solve one, what do we have to do? we can make an approximation. So we can make the approximation that a of x varies slowly. And that's kind of what we're saying with the whole system in general. If you remember the system, we're making the approximation that v of x varies slowly. So wouldn't it make sense that a of x also varies slowly? So if a of x varies slowly, we can say that a double prime is going to be approximately, not really, but approximately 0, right? Because if it varies slowly, if you take the second derivative of that, you're probably averaging out to about 0. Now, with that, we can say that 0 is approximately this right-hand side of what we wrote down previously, okay? This right-hand side, which is a p squared h bar squared plus phi prime squared. Now, what can we do from here? Well, let's kind of manipulate things to get this on one side and this on the other. So let's divide everything by a, get rid of those, and then we get something that looks like phi prime, which basically is d phi dx, if you remember, right? It's got to be. That equals plus or minus p over h. You guys see how I got there? I subtracted this on both sides, merged the minus signs, and then took the square root of both sides. Okay, that's why I got the plus or minus p over h with our phi prime. Now, what do we do from here? Again, you guys might remember, here I'll erase this. But you guys might remember this from your differential equations class, but it's pretty easy to solve from here. From here, we just integrate both sides, and we get phi of x equals 1 over h bar plus or minus 1 over h bar. Let's pull that out of the integration. P of x dx. Okay? So this is what we'll call our new phi. So this is again something that you guys should write down. That phi of x is equal to plus or minus 1 over h bar times the integration of p of x dx. Okay? And now, finally, let's wrap all this up, right? So I'll erase this. What should I erase? Let's see. I'll erase everything but what we have calculated. Okay? So we finally got down to these two equations. This equation for a and this equation for phi. Now, if you guys will recall my ansatz from before, we know that phi of x, or sorry, pardon, psi of x equals a e to the I c. You guys remember that? So with that ansatz, let's plug in our a. So if we plug in our a, we get this equaling c over the square root of phi prime. E to the I phi. So now we have everything in terms of phi. This is good, right? Because we have an equation for phi. So let's just plug that in. With that, we can have c over. Now what changes here? This phi prime, well, we know what phi prime is, right? Phi prime is just, it's basically just p. So let's write that in there, p of x. Because we can say that there's some constant, right? There's this h bar that we got to worry about, but actually that h bar, we can kind of just eliminate, we can absorb that h bar into this constant here. So let's forget about the h bar now, but e to the plus or minus I over h bar, right? We can't absorb that h bar into anything now, so we have to keep it, times the integration of p of x dx. So this equation for psi, is our equation that we're going to use for the majority of this chapter. Sorry about that. So that is our equation that we're going to use for the majority of this chapter, and it's pretty much the base formulation of the WKB approximation, right? So this is what we use. If we mean WKB approximation, this is what we mean, okay? So now, what should we do with it? Let's try to use the WKB approximation, since we just figured everything out about it. Let's try to use that WKB approximation to actually solve a problem now. So, it's all this stuff. You guys got it? Sorry. Ask your neighbor if you didn't write it down. Let's see if I can get a piece of chalk here. Okay, so we're going to do example 9.1. If you guys have your books, it's in the book. So let's assume we have an infinite square well with a bumpy bottom. Okay? Now, what do I mean by a bumpy bottom? I'm just saying that v of x is of the form this. We have some function here, f of x, right? Some function where this is where x is, so where x is in the, right, it's in the well, we have this weird function, but outside the well, we have this infinite square well thing. So let me just draw that out, right? We have this infinite square well, so we have, well, this, infinite out here, it's infinite out here. Here's 0, here's a. And we have this function that's our v. Doesn't look like it, maybe it has some curves, some kinks to it. It just kind of looks funky, right? So there's some unspecified f of x here. And now let's assume that we have a function where our e is higher. Okay? So we know our e is higher, so that should lead us into our equations that we've kind of already solved for, right? We've already gotten these equations out, so I'm just going to write them in. So we should assume that psi of x looks like 1 over square root p of x. And it's going to be some linear combination of the plus and minus states that we had before. So let's say that there's this c plus associated with the plus form, e to the I phi. And then there's this c minus associated with the minus one. Okay? So that, again, that's what we've already solved for. But if you guys remember anything about this, we can simplify this, right? If we have some linear combination of complex exponentials, we know what we can get out of this. We can, this is approximate, but anyway, we can approximate again and say, well, these complex exponentials, maybe they're trigonometric functions, right? We know that conversion, so let me just make it here for you. This C1 sine of v of x plus C2 sine, cosine of v of x. Okay? So now we have this new form. And also, I should note that we know what phi is, right? We know that phi equal to 1 over h bar integration of p of x prime dx. Right? So I'm only calling it x prime because, well, what's our bounds of integration? Well, our bounds are, it only goes from 0 to x. So if we go from 0 to where we are now, and this is the form that we've discovered earlier. But also, we know that that this function here must go to 0 at 0. So we know that psi of 0 has got to be equal to 0, right? Because in this square well, psi can't go outside here because it's infinite out here. So if psi can't go out of there, it's got to be 0 here. And if it is 0 here, we can say that, right? We can say that C2 must be 0 as well. Right? If we plug in this boundary condition, that gives us C2 equal to 0. Right? And you can see that from this cosine function here. And it's kind of similar to what we've done in the past with an infinite square well with a flat bottom. But now, here's where the interesting part comes in. Because if the astute among you would remember that also, it's also got to be 0 at A. Now, this kind of throws a wrench in our plan because we can't just make C1 0 as well because, well, then that just gives us a trivial solution. So, in reality, we must have something that gives us 0 here. So, well, maybe if this can't be 0, maybe sine of phi of x can be 0. So if sine of phi of x can be 0, and this is at x equals a, remember? So if sine of phi of x is equal to 0, what does that mean? Well, that means that this inner part has to be in pi, right? So if phi is in pi, then this sign will always go to 0. So that can help us out because we can say that now, if that gives us 0, so we can now say that this gives us phi of a equal to in pi. Okay, so that's kind of useful, right? We used a similar thing in the past to give us our final equations. Well, if I can erase this, this formulation here, you guys might be able to remember it. So hope you guys all wrote that down, but erase the formulation and then say, now let's use phi of a, right? We know that phi of a has to be in pi. So let's plug that in. And let's get 0 to a, right? We know it's got to be 0. Oh, pardon. Let me not write that. Yeah. Anyway, sorry. 0 to a, p of a, p of x prime, pardon, equals in pi. Okay, so we said that phi of a equals it in pi, so we'll plug in a for x and get in pi out, hopefully. But remember also there is this 1 over h bar here. Let's not forget it. Let's just move that all the way over here. So let's say that in pi h bar. Okay? And now this is our final formulation. This is our answer here. This gives us our quantization, and it shows us our allowed energies. And we can see that actually if we say that v of x equals 0, let's kind of try and test this out, right? If v of x equals 0, then p of x is going to look something like square root of 2 in e. Right? Do you agree with that? Because v is 0, so there's not minus this v part. We'll just take that out entirely, and we'll get this 2m e. So if you, the astute among you will also remember that this gives us the allowed energies, E of n equals n squared pi squared h bar squared over 2ma squared. And this is just the infinite square well again. So we can see that our approximation scheme will give us good answers as long as we keep our formalism right and we work it out. We can use these approximations and say that, well, it gives us the right answer for most of the time, so it's probably going to give us the answer for a lot of other times. So next class, we're going to be talking about tunneling, which we're going to consider some things in the non-classical region. So thank you very much, and hope you guys remember this stuff when you come back.